going to care about these invariants are this one that tells you the center of the Morse circle in 3 dimensions, and this other one that tells you the radius of a Morse circle in 3 dimensions. Any question? Yes.
So you said that J2 is going to show the amount of shear
Yes.
you had, but it's kind of an average shear?
It's an average shear, yes. We are putting a 3-dimensional state of stress and just calculating one number out of it. And the assumption behind that we can quantify shear with just one single number, is that we assume that our rock or our material is isotropic, which in reality, that's not the case. So for real rocks, you have to be a little bit more careful about that. And rocks may resist different amounts of J2 depending on the direction in which they are applied.
And how do you compare, for example, the J2 with the Q, for example, that is also related to
Yes.
stresses, right?
Yes, we're going in there right after I make one plot right.
Okay.
Okay. Any other questions related to I1, J2? So those are just equations that help us deal with the stress tensor.
What is J3?
J3, it will be the determinant of the SD matrix. And if you remember from linear algebra, guys, I just made my brand new Twitter account, okay? I'm gonna send you later what is my name, and I'm gonna share with you a link about it help with linear algebra. Apparently, it's a good review about linear algebra, and I'll share that with you. I don't have it now on top of my head, but if you remember from linear algebra, the determinant of a matrix with all the off-diagonal terms equal to 0 is just a product of the principal stresses. So in this case, I3 is that, and in the case of J3 would be sigma 1 minus, would be sigma 1 minus sigma m sigma 2 minus sigma m and sigma 3 minus sigma m, which it doesn't matter for now. We'll see later on that there are some advanced criteria for telling when the rock is going to fail, that they use I3. But simplified models of rock failure, they just use I1 and J2. And that's what I wanted to do right now. Why these are useful? Okay, they are useful because we like to simplify stress tensors, and instead of drawing a Morse circle with shear on the y-axis and the normal stress on the x-axis, and drawing an entire circle and saying how far this circle is, for example, to shear yield, where this is going to be, this is the equation for shear, the Moore-Coulomb criterion. Basically, you will say if the Morse circle gets closer to this line, it's going to fail in shear. And you can see that from looking at the circle from this line, right? Well, when you go into 3 dimensions, it gets a little bit more complicated. And instead of doing this, what do you think we could do in order to plot something very similar? What should I plot here in x-axis. What would be the equivalent of the level of normal stress? The first invariant I1, and on the y-axis, the amount that quantifies shear, we say, is going to be J2. And similar to this, we can also draw a line that tells me what is the maximum J2 so that I do not get to shear yield. And that will depend on, in this case, it's just a linear relationship between J2 and I1. Yes?
And this would be more called failure criteria also, but written in terms of the invariants, right?
Yes, correct.
Okay.
It's a failure criterion. We're going to go more in detail about this later on, but here I'm just giving you, it's exactly the same as this one. Just the parameters are different. So S0 and mu, which in this case is friction coefficient, is going to convert to C0 and C1, but it's the same thing, just different numerical value. Yes, Stephanie.
What is on the third axis if this is 3D?
Which third axis?
So this is a 3D
this.
Morse circle?
So here, this is going to be a point. Instead of a circle, we're just going to have a point. What?
This is a 3D Morse circle. So
No,
there's,
well, this is a 2D Morse circle.
Right.
We could make it 3D. Let's do it 3D. And we are simplifying this 3D Morse circle into just one point as a function of I1 and J2. So it's just a way of simplifying a full stress tensor in two numbers, but two very meaningful numbers, because this one tells me about the level of compression, or some people may like to call it confinement, and this one tells you about the level of shear. And let me give you one example here. Probably, if some of you come from a mechanical engineering background or from a civil engineering background, probably you saw that there are some materials, like metals, in which, for practical applications, it doesn't matter what is the value of I1, you just care about the value of J2. If you pass some value of J2, then the material fails. But for rocks, it's very important because the more confinement or the higher the effective mean stress that you have, the rocks become stronger. And that's something very important to consider in practical applications. Jackie,
Yes, so on the plot on the left, we don't draw it more circle. It's been converted to dots on the plot.
Yes, correct.
Okay.
Correct. Yes. Okay. So I know that James has to leave now. So I like that we talk at some time and we can find a common solution. Okay.
Yeah.
But for this time at least, let's just keep it going as we go.
I'm just watching the lectures online.
Okay. Okay. All right. So that is one way of simplifying a stress tensor. It is very useful because, for example, if I wanted to plot something which is called a stress path, it's just going to be dots that move in a certain direction. And it would be extremely difficult to do that with a Morse circle. You imagine me plotting like several Morse circles, one on top of each other. It's going to be, especially if the three quantities change, it's going to be very hard. And sometimes we like to draw these stress paths because, for example, we can have time changing in that direction. So we know that, for example, if we have a reservoir that is being subjected to depletion, as time passes by and stresses change, the state of stress is going to change. And if it approaches some yield limit, we can plot that very well with this type of plot. So let's do another type of, or let's write another quantity that is very similar to J2 and I1. Usually J2 and I1 are used in material science and a little bit on rock mechanics, but not that much. Instead, what we use in soil and rock mechanics are two other parameters. So in soil mechanics and rock mechanics, instead of J2 and P, we're going to use a variable called P prime. And this P prime is just equal to the effective mean stress. And now I'm going to emphasize that this one is effective. It was always effective, okay? But I just didn't emphasize that before. And as we said before, that's going to depend on the invariant number 1. So this is going to be the invariant of the effective stress tensor divided by 3. And the other quantity that we're going to use is a parameter called Q, which is going to be equal to the square root of 3 times J2. And the advantage of these two parameters is that for certain conditions in which we have a principal stress sigma 1, let's say, and sigma 2 and sigma 3 that are the same, this is a case that you find in axisymmetric stress conditions, then Q is going to simplify a lot because now it's going to be square root of 3 times J2, and that J2 was sigma 1 minus sigma 3 squared, and sigma 1, wait, I'm forgetting here another bracket. Sigma 1 minus sigma 2 squared, and sigma 2 minus sigma 3 is going to be 0. So I'm not going to write it. It's just these two. And if you do a little bit of algebra, you will see that this is going to be 1, this is going to be 2. Sigma 1 minus sigma 3 is the same as sigma 1 minus sigma 2 because sigma 2 is the same as sigma 3. So this, let's call it 2 sigma 1 minus sigma 3. And 2 and 2, they cancel out. And since this is squared, this is equal to sigma 1 minus sigma 3. And this guy, P, still has the same name as that. It's called mean effective stress. And this amount over here usually just goes by Deviatoric stress. So the deviatoric stress tensor was the one that we saw before. This one over here, but this is a full tensor. This one is just deviatoric stress, and it quantifies how much shear you have, and it's equal to the difference between the maximum stress and the minimum stress. You can go a little bit further, and assuming these axisymmetric conditions, also we're going to have that P is going to be sigma 1 plus 2 times sigma 3 divided by 3, and Q, I'm going to write it again, sigma 1 minus sigma 3. And this is going to be the equivalent to our parameters I1 and J2. And what do we do with that? Well, exactly the same that we did before. We like to plot these two quantities with the normal component in the x-axis, the shear component in the y-axis, and usually here we may have a limit for shear failure, and I'm going to have another limit, but I'm not going to write it right now. Let's say that this is our initial state, and we're interested in how that varies with time. So let's make an example. Let's say that, as we were saying before, that you're interested in a place in which there's going to be a well that's targeting a reservoir in some particular location, and we're interested in knowing how the state of the stress is going to vary in this location. So if we have an initial state of stress and change the conditions